Ladies and gentlemen, my name is Andrzej and I represent Silesian University of Technology, Poland, and I would like to present my common study with Dr. Sandris from Riga Technical University, Latvia, which is focused on damage identification in composite structures using two different approaches. The first one is based on damage indices, and the second one is based on curvelet transform. During the study, we will compare the effectiveness of both of these approaches. Here you can see the outline of this presentation, so I start with an overview on structural damage identification and in particular vibration-based methods. Then I will tell you a few words about processing, which is necessary step to identify damage in such structures, and finally present you some results of comparison of approaches based on damage indices and curvelets. Considering the modern trends in maintenance of mechanical and civil structures, NDT seems to be very important step of this maintenance. And that's why there are a lot of NDT methods developed to date to do such inspections. You can see some groups of these methods on the screen. It is, of course, not the complete list of these methods. There are many more, but these are the most widely used. Vibration-based damage identification methods, although the oldest from NDT methods, are still effective and are still used in identification of damage in mechanical and civil structures. Mostly they are based on model analysis from which we can get three types of parameters: mode shapes, natural frequencies, and coefficients of damping. Mode shapes are the most sensitive of these parameters, and with appropriate precise measurements, I mean here non-contact measurements, for example with use of laser Doppler vibrometry, we can get very precise information on vibrations of a tested structure, and with appropriately selected processing methods we can get specific information about not only the presence of damage, I mean not only the detection, but also the localization, so telling where the damage is located, and identification, so what is the type of damage. So we need appropriate processing of our mode shapes to get this information. In vibration-based damage identification, we have generally two approaches: the reference-based approach, which is based on the intact structure or model of the structure, or reference-free approach, which is much more effective since we are operating only on a damaged structure. And we have two sub-approaches. In the case of reference-free methods, the approaches based on damage indices and the approaches based on various types of transforms. There are numerous formulations for damage indices used in damage identification problems, but in this study we are basing on the approach proposed by the team from Riga Technical University. So the damage index defined by the coordinates S and P is a sum of displacements for these coordinates and the given mode squared divided by the maximum value squared of this displacement. Further, for further consideration, we consider the standardized damage index, which considers also the mean value and standard deviation. So assuming that as the eye is normally distributed, the probability density function may be used to classify elements by employing a one-tailed hypothesis test. And you can see these two relationships for defining this hypothesis. CR is the predefined probability threshold. We considered here three thresholds. It is 1.28, 2, and 3, which corresponds to 90, 95, and 99 confidence levels for the presence of damage. The objective of the hypothesis is to decide whether the element of the structure is damaged based on the significance level or not. Another approach is based on space frequency transforms, and one of the most widespread is the wavelet transform with several modifications of the basic one, but the general idea and advantages of this transform is the possibility of adjusting a Bayesian function to a tested signal, multi-resolution analysis, and sensitivity to damage. But we have several disadvantages of wavelets. I mean here lack of directional selectivity, susceptibility to noise, and boundary effect. To overcome these problems, we proposed using curvelet transform for processing. So here you can see a typical decomposition based on separable wavelet transform, but in curvelet transform the decomposition looks a little bit different. You can find some theoretical fundamentals in our paper, but what is important from the point of view of our analysis that the curvelet transform gives us the possibility of directional selectivity, and also it is very good filter of noise, so we can obtain very well denoised results. In the slide you can see the tested structures, 3 cases. There were GFRP structures with mild damage according to the schemes you can see on the slide, and the tests were performed with the laser Doppler vibrometry, where we measured in non-contact way the vibration velocities, and based on the acquired mode shapes for the considered plates, we performed further analysis. And here you can see the results obtained using the damage indices approach for case A, so the case with the through the width crack. Always these results will be presented for different levels of confidence, so 90, 95, and 99%. In all the cases, we can see quite well the damage, but also we can see some additional noise resulted from measurements and processing. Here you can see the results for case B, so we can quite well identify the shape of a square damage introduced to this plate. And finally, case C, where we have a multi-damage case, we can see quite well the square damage, the bigger square. We can barely see the lower square, but we don't see well the crack, the third damage. Moreover, we can see here a lot of false detected damage, so a lot of pixels that show some increased amplitude, but which are not attributed to damage. In this slide, you can see the results obtained using curvelet transform. So in all the cases, you can see that the quality of results is much better. We have a lot of noise. We can see some noise on our resulting maps, but the coefficients in the locations of damage are much higher in magnitude. So, for example, in case C, we can easily identify all 3 introduced damage sites. As one can see, the processing of mode shapes is a very important step, which can show us much more information about state and condition of the structure than the raw data, but it is also very important to appropriately select the methods of processing. So as you can see during this presentation, when we compared the results of damage indices approach and curvelet transform approach, we can see that curvelets gives us much better results in terms of visibility of damage and in terms of reduction of noise. So the xlets, not only curvelets, but the larger family of xlets create new possibilities for further enhancement of the damage detectability to increase its sensitivity and can be widely used in many NDT and SHM applications. The observed precision in damage identification makes it possible to even quantify damage, which will be the subject of our further investigation. Thank you very much for your attention.